Hello, welcome back to my lecture. This topic is NMOS inverter driven by another inverter. You can see here there is a NMOS inverter shown here with pull down device as NMOS transistor, and pull up device is also NMOS depletion mode device, which is NMOS inverter. This NMOS inverter driven through another inverter. Then what is the transistor size? Now, to cascade the inverters without degrading the output levels, the condition is V in is equal to V out. Both must be equal to V INV, inversion voltage, which is considered as 50% of the supply voltage, 0.5 VDD. So, in this condition, both the transistors will be in saturation. When both the transistors are in saturation, the current equation for the transistors in saturation is IDS is equal to kW by L into VGS minus VT whole square by 2. This is the standard condition for enhancement mode transistor. For depletion mode transistor, IDS pull up device is equal to kW by L, because VGS is 0 in the pull up case because its input is connected to ground. So that is 0, that is why it is PTD minus PTD whole square by 2. This is standard equation. Because we have already told for good output, V in should be equal to 50% of VDD, which is equal to Vi and V. Input is connected to the enhancement mode transistor. So enhancement mode transistor gets 50% of VDD, which is VINV. That is why it is written as VINV, and here it is VTN, VIN minus VTN, because here we wrote pull up device width and length. Here it should be pull down device width and length. Because both the devices are connected in series. In series, currents will not change, same current will be there. So these current equations which we have just now seen, both the currents will be equal. So as both the currents are equal, we can equate these two terms. Now, by equating these two terms, the common things are k gets cancelled. When you see L by W is equal to Z, which is a parameter representing the dimension of the device. So this ZPD, pull down device Z, is equal to L by W, and here also L by W. So this Z is called as aspect ratio. Here it becomes 1 by ZPD. Here it becomes 1 by ZPU. Rest of the thing is same. When you equate and try to simplify this equation has become VINV is equal to VTN minus VTD by under root ZPU by ZPD. This is the simplified equation. Now substitute the values of VTN and VTU, VTP, the typical values. Now typical values for VTN is equal to, as just now in the previous lectures also we have seen, the typical value of VTN is 0.2 VDD, and VTD is equal to minus 0.6 VDD. That means if you apply, for example, if the VDD is 5 volts, it should be minus 3 volts and above to make the device off. So that is VTD. VTD is equal to 0.6 VDD. And VINV is, as we know, 50% of the supply, that is 0.5 VDD. Keeping these terms, substituting all these terms in that equation, we got pull up to pull down ratio of NMOS inverter driven by another inverter is 4:1. This is in one situation. In the other, this is one case. Now case 2 is NMOS inverter driven through one or more pass transistors. What is pass transistor? Pass transistor will be a horizontally connected transistor whose gate controls whether to pass or stop. When the gate is connected to supply voltage, transistor turns on. Whatever the voltage that is available here will be transferred to this point. If this is also on, it will pass through like this. When the condition is, if all the pass transistors gets a logic 1 as the input, then only the output of this inverter reaches the other inverter. But here the problem with the pass transistors is pass transistors passes 0 well, it passes good 0, but it cannot pass good 1, because it will consume Vt as the threshold voltage. Threshold voltage will be consumed. If the input is VDD, then the output will be VDD minus VTP. That is the problem with pass transistor. Now let us go deep into this. Pull up device is in saturation, so the device can be considered as current source. Pull down device will be in linear region, that can be considered as a resistor. Now for the pull down device, if you write the equation, IDS is equal to, because we have considered pull down device is in linear region, the current equation for the linear region is kW by L into VDD minus VT into VDS minus V square ds by 2. This is standard equation which we have learned in VLSI design as well as in the previous lectures also, previous topic also. So that is, by this equation, if you need to estimate the current, you have current and you know what are the voltage that are applied. Now we want to estimate, we just need to estimate the resistance offered by the device. R is equal to V by I. R is equal to R1 is equal to VSD of device 1 first inverter by IDS of the device 1. So by applying and cancelling, by substituting and cancelling this, we will get VDS by 2 as a factor, this VDS by 2. Consider this as a factor, and because VDS is small, divided by 2 is even more small, so neglect that. If you neglect that, R1 becomes L by W is Z, 1 by K is Z by K, 1 minus, this is neglected, VDD minus VTN is left. This is for pull down device. Now pull up device, whose VGS is 0. Whose VGS is 0. So as VGS is 0, the term before this, like this, VGS will be here, that term is 0 to this. Now just you can write I1 current. This current is same to this device, enhancement device, as well as depletion device. So I1 directly taken without this VGS, and I1 R1 is equal to output. After, between pull up and pull down device, there is a connection that we take as output. So output is equal to, this is ZP, 1 by ZPU, that is why ZPU comes here. It is K, and it is here, it is K is in denominator, those will get cancelled. So ZPD by ZPU into 1 by VDD minus VT into VTP by 2. This is output 1. That output has to be applied to applied as input to the second inverter. So this is output 1. This should be given to the second inverter. When this is driving the second inverter, Vout2 will be I2R2, where R2 is, as we did with the previous case, R2, we have got, we will get R2 like this, and I, current equation, input is 0, that pull up device. So the current I2 is given like this. So the final output Vout2 is I2R2, which will be this quantity ZPD2 by ZPU2 into 1 by this parameter and multiplied with this parameter. When for a good inverter, output of inverter 1, Vout1 should be equal to Vout2. When Vout1 is equal to Vout2, I1 R1 can be made equal to I2 R2. If by substituting the terms of I1 R1 and I2 R2 here, this is I2 R2. Here what will you get? You will get a equation like this, in which the dimensional parameters Z, aspect ratios, comes with some parameters whose typical values can be substituted for simplifying the equation. Now applying that typical values, as we have discussed already, these typical values after substitution, you will get a ratio of 8:1. Now the final statement is, if an NMOS inverter driven through one or more pass transistors, when an inverter is driven through one or more pass transistors, it should have an inverter ratio of 8:1. Previously, when an NMOS inverter is driven through another inverter, then the aspect ratio, pull up to pull down ratio is 4:1. If it is through one or more pass transistors, driven through one or more pass transistors, then the aspect ratio must be 8:1. These are the transistor sizes in different conditions, and this is the switching characteristics of a CMOS inverter. The switching characteristics of CMOS inverter can be explained by the help of this diagram. This is one CMOS inverter and this is another CMOS inverter. In between these two there is a load capacitance CL. Now how the load capacitance is charged and discharged, that shows you the switching characteristics of the CMOS inverter. Now these switching characteristics can be explained with the help of these considering all the capacitances, parasitic capacitances that are corrected. VGD, gate to drain capacitance. Because some part of the gate is overlapping the drain region, there is a capacitance formed which is called as VGD, and similarly a little part of the gate overlaps the source also, that forms this gate overlap with diffusion capacitances. CDB and CGB, DB and GB, CDB and CGB, gate to substrate, drain to substrate, source to substrate. These are the voltage dependent junction capacitances. And Cout is the output capacitance, which is not shown in the diagram. CGN and CGN and CGP is thin oxide capacitance over gate. This is gate structure, this is thin oxide. Because of this thin oxide, a channel capacitance forms, which is this. CL is the output capacitance, which is the lumped parameter with CDGN and CDGP and CDT. So with this is the inverter, and these are the delay parameters. When the input takes a transition from 0 to high, output takes a transition after a little delay. That means when the input crosses 50%, it starts transition, and a delay of 0 T0 to T1 happens. These are the delay parameters of a CMOS inverter. The delay is counted using delay time TD. It is the time difference between the midpoint of the input swing and the midpoint of the output swing. That is delay time. The delay time estimation can be made with the help of the diagram. With the help of this diagram, the delay time estimation can be made very simply. The pull-up device acts as a current source and pull-down device acts as a load capacitance. By substituting the dimensional values of pull-up device and pull-down device, so the delay time is RC time delay. We already know the value of resistance RL R resistance offered by the device R, and we know the capacitance CL. Just now we have discussed in the previous slide. Putting those two terms, this already we have derived in the previous section. uh, so T is always equal to the product of R and C. So this is R and this is C. The R and C together gives you this delay parameter. How much delay that a CMOS inverter introduces to change its output when the input is changing. This is delay switching characteristics. I hope you understood. Thank you.